Welcome. In this lecture, we shall solve the last of the problems based on bending stresses in beams. The problem is given as a beam of I section having top flange 100 mm by 20 mm, web 20 mm by 100 mm, and bottom flange 180 mm by 20 mm is supported on an overhang beam with loading as shown in the figure. Calculate the maximum value of W in kilonewtons if available bending stresses are 35 megapascals in tension and 45 megapascals in compression. Find also the radius of curvature at midspan for maximum load W. Take Young's modulus of elasticity E as 200 gigapascal. Let us first write the given data. Then the parameters to be found out are written next. We now draw the beam cross section as per the dimensions given. Using the formulas to find the centroid and the area moment of inertia about the centroidal or neutral axis, we get the respective values as y bar from the bottom is equal to 57.37 millimeters rounded off to 2 decimal places. Hence, y bar from the top is equal to 82.63 millimeters and I about the neutral axis or x-axis is equal to 20.8 times 10 to the power of 6 in millimeter to the power of 4 units. Now let us draw the bending moment diagram for the given loading on the beam. We find that the bending moment is maximum positive, that is of sagging type at the center of the beam, that is at point C of value plus W kilonewton meter. The bending moment is also found to be maximum at 2 points of symmetry, one each at the supports of hogging type, that is at points B and D of value minus W kilonewton meter. We shall consider either of points B and D, say point B for hogging and point C for sagging for our calculations to find the maximum value of load W. In general, we have M over I is equal to sigma B over Y as part of the flexure formula. Now, starting with point B, the top layers experience tension while the bottom layers experience compression. We will disregard the negative sign of the maximum bending moment for our calculations, which isn't really necessary as such. Hence, for the topmost layer in tension, Mmax, that is W kilonewton meter times 10 to the power of 6 converted to Newton millimeters over I, which is 20.8 times 10 to the power of 6 in millimeter to the power of 4 units, equals sigma T, which is 35 megapascals over Yt, which is 82.63 millimeters. We get W as 8.81 converted to kilonewton meter units. Let's call this as equation 1. For the bottommost layer in compression, Mmax, that is W kilonewton meter times 10 to the power of 6 converted to Newton millimeter over I, which is 20.8 times 10 to the power of 6 in millimeters to the power of 4 units, equals sigma C, which is 45 megapascals over Yc, which is 57.37 millimeters. We get W as 16.31 converted to kilonewton meter units. Let's call this as equation 2. Now, considering the midspan point, that is C, which experiences maximum sagging, the top layers experience compression while the bottom layers experience tension. Therefore, for the topmost layer in compression, Mmax, that is W kilonewton meter times 10 to the power of 6 converted to Newton millimeters over I, which is 20.8 times 10 to the power of 6 in millimeter to the power of 4 units, equals sigma C, which is 45 megapascals over Yc, which is 82.63 millimeters. We get W as 11.32 converted to kilonewton meter units. Let's call this as equation 3. For the bottommost layer in tension, Mmax, that is W kilonewton meter times 10 to the power of 6 converted to Newton millimeters over I, which is 20.8 times 10 to the power of 6 in millimeter to the power of 4 units, equals sigma T, which is 35 megapascals over Yt, which is 57.37 millimeters. We get W as 12.69 converted to kilonewton meter units. Let's call this as equation 4. Instead of comparing the results based on sagging or hogging separately as we did in the last solved problem, here we compare the W value from the 4 results instead and select the lowest value of all. Hence the maximum or safe value of bending moment, that is W here, is not expected to exceed 8.81 kilonewton meter. In terms of the load units, the maximum load W is hence 8.81 kilonewtons. Now to estimate the radius of curvature R, we use the other part of the flexure formula, that is M over I equals E over R. Therefore R equals E times I over M, which is found to be 472.19 converted to meter units. To summarize, we have maximum W equals 8.81 kilonewtons and radius of curvature R equals 472.19 meters. In the next lecture, 3 problems, that is 8, 9 and 10 shall be provided for practice based on bending stresses in beams.